In this video, we're going to take a look at the application of Neuber's rule to cyclic loading and then the subsequent application of some strain life damage parameters that are mean stress sensitive. This particular example is 4.30 out of the Bannatyne text, and we'll take a look at a couple parts of this, probably history A and history B, to kind of get things set up. Probably leave history C for you to do on your own. But this problem says a notched aluminum component consists of a 12-inch wide by 1-inch thick plate with a 2-inch diameter hole. Determine the life of the component under the axial load history shown below. History A is constant amplitude 0 to maximum. Histories B and C have initial overloads followed by 0 to maximum axial load. For this problem, use a Neuber analysis and predict lives using the three mean stress relationships, equations 249, 250, and 252, which I have copied over there to the second column. And here are the material constants and the strain life constants for this. It says actual test results are given below for the three load histories. 4 tests were run for each of the histories. Compare these values to the lives predicted in the first part of this problem. Note that the test results are given for crack initiation life, and this is done since the strain life approach is considered to give an estimate of crack initiation life. Now, also associated with this, I have shown the stress concentration factor plot with the dimensions indicated. W is the entire width of the plate, P is the axial force, D is the diameter of the hole, and we have the D over W ratio, and to which we can find the stress concentration factor KT. Now, if we had KF, the fatigue notch factor, then we could use it. Lacking information about KF for this particular problem, we're going to use KT. And so the version of Neuber's rule that we're going to use is going to look like this. The notch root stress and strain is going to be equal to KT times the nominal stress S times KT times the nominal strain, little e, or KT S squared over E, where S is going to be the nominal stress as is defined in this particular problem statement with this figure. So on our first excursion from 0 to 240 kips, we'll use the monotonic version of Neuber's rule. In the next steps, we'll use the cyclic version of Neuber's rule. So let me write that down as well. For the cyclic version, basically we're just going to replace the stress and strain endpoint values with the stress and strain ranges. So this will be like delta sigma, delta epsilon. You think of them as amplitudes, but then the 2's all divide out. It's going to be a KT squared, and I need a squared right here as well. KT squared delta S squared over E. And in addition to this, we're going to need the relationship between notch root stress and strain, which is the sigma and the epsilon. In which case, we're going to have epsilon is equal to sigma over E plus sigma over K, but we're going to use K prime if it's a cyclically stable material, to the 1 over n prime power. And then similarly, delta epsilon, I like to write it in amplitudes first. Delta epsilon over 2 is equal to delta sigma over 2e times delta sigma over 2 k prime to the 1 over n prime power. Or if we solve this for the strain range, we're going to have delta epsilon is equal to delta sigma over E plus 2 times delta sigma over 2k prime to the 1 over n prime power. And again, we pointed this out before, but notice how the 2 here cancels out, but this 2 does not cancel out with that 2 because the second 2 is inside of the parentheses and it's taken to the 1 over n prime power. Alright, so with that information, we're going to get started on this. And again, like I said, we're going to take a look at part history A first. Let's go ahead and figure out the stress concentration factor while we're on this page. And in order to do that, we need to find the ratio of D over W as it's defined in this picture. So D, they said it was a 2-inch diameter hole, so that's the little d, and the W is the width of the plate. So that's 12. So that's a sixth. What's that? Let me get a number here. 0.1667. All right, so here's 0.1. Here's about 0.15. 167 is maybe just a little bit over from this. So if I take a line, it's hard to get a straight line on this. Let me see if I can use this tool here. And then bring that intersection point over. Trying to get it as horizontal as I can. Here's 2.2, 2.4. I'm going to call it 2.55. Maybe a little bit less. Maybe 2.52. Alright, so we'll use that number for this example. Now you may read this chart just a little bit differently than me, and so you may end up with a little different stress concentration factor value. Alright, the next thing that we need to make note of is what the definition of the nominal stress is. In this case, for part A, I don't know if you can see that right here, the nominal stress is the force divided by A, where A is defined as W minus D times T. So now W is 12, and the diameter of the hole is 2, so that looks like 10. So S nominal is going to be equal to P over 10 times the thickness. It's 1 inch thick plate. Okay. So let's make a note of that on the next page. And we're going from 0 to 240 kips of axial force. So in our initial step, we're going to go P is equal to 240 kips. All right, so in this case, our S is equal to 24 KSI. We said our KT that I'm going to use is going to be 2.52. Again, you might have a little bit different KT. We need some material properties now. .6 times 10 to the 3 KSI, K prime and N prime. Let me write those down on a piece of paper, and then I'll write them down on the previous, on that next page that I showed. .95 KSI and 0.065 for my exponent. All right, so let's set up our equation. So our time history, the initial step is going to be from 0 all the way up to 240 kips. All right, so let's see. We have sigma times epsilon. So on the left-hand side, I'm going to have a sigma squared. I'm going to leave this as the symbol E, but we know what that value is. Then we're going to have a sigma times a sigma over k prime to the 1 over n prime power. And on the right-hand side, we're going to have our kt squared, our s squared. I'm going to do everything in KSI units. And then our modulus of elasticity, E. Again, I'll leave that as a symbol. Now, in order to find our stress, we're going to have to use a root solver. We can do a Newton-Raphson technique as well. And let's write down what our function would be for the Newton-Raphson. We'll do this in terms of symbols in case you want to program this in. And then, of course, our df by d sigma is the variable we're wanting to solve for. We're going to have a 2 sigma over E. We're going to have a product term. We have the derivative of the first times the second term. And then we're going to have the first term times the derivative of the second term. And then we have the term in parentheses. And we're going to take away 1 from that. All right. And then the last term, it has no sigma in it, so its derivative vanishes. And so what we're going to try to do is we're going to try to guess our sigma, calculate our f and our df, and then make a new guess based on that ratio. New guess is our previous guess minus f over df. Of course, if we were to exactly guess the right sigma on the first try, then our f would go to 0, and our new guess would not be any different than our old guess, and then we would have converged. But what you can do is you can set a convergence criterion. You can also use a spreadsheet and use the solver as we talked about previously in Excel. All right, let me pause the video here and let me put this into my own spreadsheet and let's see what we get. All right, so in my spreadsheet, I'm going to set this up so that I'm going to be able to use the solver inside of Excel instead of the Newton-Raphson technique. I think that's fine. So here's my KT, here's my dimensions, here's my material properties. My applied force 240 kips, nominal stress is automatically calculated based on the A. Here's the KT squared S squared over E value. Here's a guess at sigma, and here's the product of sigma times epsilon, the notch root stress and strain. So if I were to guess the right sigma and I were to subtract these two terms, this one here and this one here, then that's this term, then I would, if that equals to 0, if I can drive that equal to 0, then I should find the right value of the stress sigma. Okay, now this is a new install of Excel for me, so let's go through the process of making sure Solver is available. So this is Office 365. So I go to File, and then all the way down here under Options, and let's see, should be add-ins. There we go. Here's our solver add-in. So we're going to hit go for that, I believe. Okay, and I just like to add the analysis tool pack and this stuff as well as the solver. So again, I think I mentioned this previously, but the analysis tool pack can help you do some statistical analysis and things like that. So I'm going to hit go or OK. All right, now it should show up, I believe, on my data. And here it is over here. Here's my solver. So let me go with solver. Okay, and so I'm going to set the objective, which is this cell, equal to a value of 0 by changing the cell with my guess for sigma. I better get rid of that. There it is. Okay. And I don't really have any constraints. There are some options here. I think this is probably fine. And I'm going to hit solve. And this looks like it's probably okay. So I got 57.9, you can call it 58 for my sigma. And here's my notch root strain, 0.05958. Make sure I'm calculating that properly. Taking my sigma over E plus sigma over K prime to the 1 over N prime power. All right, so I think that is my answer for the first part, where I go from 0 to 240 kips. Let me check that, and if there's any issues, then we'll update that. All right, so I think those numbers look good for the initial 0 to 240 kip loading. I added another column to put in microstrain right here. So let me go back to our sketch pad here. And let me add another window. And what we want to do is we want to plot the stress strain response at the notch root. So this is the sigma and epsilon plot. All right, so I said 57.9 for my stress. Now, whatever that looks like, this is just a sketch. So 57.9, and you know, usually you plot X and Y. I'm going to label this as my sigma and then my epsilon. In microstrain, 4 digits is probably pushing it, but we'll call it 5958 anyway. .58 microstrain. Now, of course, in order to get the strain at the notch root, you know, like I said, I think I already mentioned, then using this value of sigma that causes this to converge, then you have sigma over E plus sigma over K prime to the 1 over N prime power. All right, so that should be what the start of this thing looks like. Now let me go back a page or two, maybe, and take a look at what happens next. So in history A, we went from 0 to 240. Now we're going to go from 240 down to 0. That's going to be a delta P of 240 inch-pounds. Let me make another one here. not inch pounds, but 240 pounds, 240 kips rather. Now, for that delta P, then we're going to have a delta S of 24 KSI. And now we're going to use the cyclic form of Neuber's rule. Delta sigma delta epsilon is equal to KT squared delta S squared over E. And we've already written this down, but we're also going to use delta epsilon is equal to delta sigma over E plus 2 times delta sigma over 2k prime to the 1 over n prime power. So let me take a look at my spreadsheet, and we're going to adjust some values, and we're going to check those formulas. All right, so now we're at the force range. Okay, so I've worked some of this out previously, but we're at 240 for a force range. That gives a nominal stress range of 24 KSI. The cyclic Neuber's rule, let's make sure that I have this right. So it's KT squared times, now this is the delta S squared, over, let's see, it says 2E. Let me check that out. All right, so where that comes from is by rearranging this formula by inserting the delta epsilon in here. We get delta sigma squared over E plus 2 times delta sigma over 2k prime to the 1 over n prime power is equal to KT squared delta S squared over E. If we go through and divide all the terms by 2, we can get it in this form: delta sigma squared over 2E plus delta sigma over 2k prime, the 1 over n prime power is equal to KT squared delta S squared over 2E. All right, so that's where that 2 came from in my formula. Now, there are many different ways to write these formulas, so just be careful and make sure that you've done the algebra to make sure everything is consistent. Let me check my spreadsheet again, just to make sure I haven't made any other mistakes in here. That wasn't a mistake, but just something we need to be aware of. So on the on this side, and tell you what, let me, to make sure that's clear, I'm going to put in here that I'm looking at the KT squared delta S squared over 2E. KT squared delta S squared over 2E. Okay, we're good on that. And then over here on the notch side, let's see if I have it according to my formula. I should have a delta sigma squared over 2E, delta sigma squared over 2 times E, plus delta sigma times delta sigma over 2k prime to the 1 over n prime power. All right, so I think I am consistent with that. So now what I'm going to do, here's my difference. Basically my left and the right hand sides. I need to drive this to 0 by using my solver. I'm going to drive M17 to a value of 0 by changing cell I17. Okay, so let's see what I got with that. Now I have a local stress range of 60.48. Let me write that down. So that's a delta sigma of 60.48 KSI. We'll probably call that 60.5. A corresponding strain range, let me label that over here, of 5706. So that's my delta epsilon. All right, I've got those written down. So I'm going to go back to this page. Now this was a decrease in load. So what that means is we're going to have a decrease in stresses and strains. So we're at 57. Let me see if I can fix this pen. All right, there we go. We're currently at 57.9, and we're going to take away the delta sigma. Which I got 60.5. So we go a little bit negative. I got minus 2.6 KSI. And let's see, our strain is our starting strain of 59.58 minus our delta epsilon, which was 57.06. So I end up with 252 microstrain. So let's see, my stress is a little negative, and my strain is a little positive. So maybe something like this. So I'm at minus 2 point, this is not the scale, it'll be very close to the edge here. It's probably steeper and everything, but you get the idea. There's my stress there, and my strain is 252 microstrain at that particular point. All right, so now the next step is going from 0 up to 240 in the nominal load. Okay. So from 0 to 240, I'm going to have a delta P of 24 kips. I'm going to have a delta S of 24 KSI. I'm going to apply these formulas again. I'm going to get the exact same values for stress range and strain range as I had previously, except now I'm on the upslope. All right, so I'm at minus 2.6 KSI. I'm going to add a delta epsilon of 60.5. Right, so delta sigma 60.5. I'm going to be at 57.9. And for my strain, I'm down at plus 252 microstrain. And then I'm going to add to that 5706 microstrain. $59.58. All right, so what this means is now I have a loop that looks like this, and it just keeps going back and forth around that loop. My strain range for that loop is the 5706 microstrain. My maximum sigma is 57.9 KSI. My minimum is minus 2.6 KSI. My stress range is 60.5. My stress amplitude is 30.25. My mean stress, 57.9 plus negative 2.6, divide that by 2, should be 27.65. And we ought to be able to calculate the maximum again by taking the mean and the amplitude. So 27.65, and I'm going to add 30.25, and I get 57.9, and that does check out. And while we're here, we might as well calculate our strain amplitude. Be 5706 divided by 2, 2853 microstrain. All right, so with that information, I should have enough to be able to use my different mean stress sensitive damage parameters. And for that, I'm going to set up either another spreadsheet, or I'll set up this spreadsheet that I have to do a little bit more work. Let me pause the video and I'll do that. All right, let's see if I have all this set up. Now, I had done a previous example, problem 2.38, in which I programmed in, or at least put into Excel, Manson, Halford, Morrow, and Smith-Watson-Topper damage parameters 2.49, 2.50, and 2.52 out of a Bannatyne book, those equation numbers respectively. Now, let's make sure I have everything right in here. And let's see. Bring up my sketch pad. And I want to check the material properties that I'm putting in. Okay, so 10.6 times 10 to the 3 KSI. All right, that's good. Sigma F prime is 160. Epsilon F prime is 0.22. B is equal to minus 0.124. And C is equal to minus 0.59. Now, what I've done is I've copied these into these other spreadsheets as well, and so I think I am okay. So next thing we need to check is we need to check our mean stress. And if we go back to here, so the mean was 27.65 KSI. 27.65 for the Manson-Halford. All right, let's check our Manson-Halford equation. I have them written here. This is 2.49. So here is my my input. It says strain amplitude, so that's H12 minus F12. Make sure that I have this set up right. Okay, so here's my strain amplitude, 2853, and that's what I had over here, 2853 microstrain. All right, now my left-hand side is my strain amplitude. So that's this term right here. Okay, so that's good. My reversals is just whatever my input is, my guess. And then the right-hand side of the strain life equation, this big long thing here, it should be sigma f prime 160 minus sigma naught over E times 2NF yeah, that's this one right here, 2NF to the B power, should be the purple one, plus epsilon f prime times 2NF to the C. Let's see, what's going on here with that? Looks like that's a different one. It actually looks like equation 250. Okay, so I think I labeled these wrong. So this is 250 is the Manson-Halford. And the Morrow should be this one. Okay. So let's take a look at the Manson-Halford. 250 is epsilon f prime times quantity sigma f prime minus sigma naught over sigma f prime to the C over B times 2NF to the C. The Morrow sigma f prime minus sigma naught over E 2NF to the B plus epsilon f prime 2NF to the C. And then the Smith-Watson-Topper would be sigma f prime squared over E 2NF to the B 2NF to the 2B plus sigma f prime epsilon f prime 2NF to the B plus C. All right, so I think I have these in here. Well, let's look at the Manson. Well, let's see. Let's do this. Paste those values in here, and we'll start with the Morrow equation. And what I'm going to do is I'm going to use the solver. I'll get rid of this 2.38. What we're going to do is we're going to do the solver, and we're going to drive this error term to 0 by changing this cell. think that's as close as we're going to get. Let's see. Make sure I'm driving my correct cells here. So drive J12 to 0 by changing the value of G12. Okay. So I think that's okay. We'll find out. So we don't deal with fractional reversals by any means. So when we come up with the reversals to failure, then we have to divide it by 2 to come up with the cycles to failure. All right, so now let's take a look at Manson-Halford. Hopefully we'll get something close by. Here's our mean stress. Here's our input. Now we're going to use our solver again. We're going to drive J12 to 0 by changing G12. Okay, and we get this number of cycles to failure. And then for Smith-Watson-Topper, we need to input the maximum stress. The maximum stress was 57.9. Strain amplitude was 2853 microstrain. Yeah, we should not get a negative number. Need to find out what's going on with that. Let me pause. Okay, I took a new guess, and I think that drove me in a better direction. So now I have this for my cycles to failure. All right, let me write these numbers down, and let me check with some work I've done previously. So Smith-Watson-Topper, 3.415 times 10 to the 4. Morrow, 1.145 times 10 to the 5. And Manson-Halford, 9.034, 035 times 10 to the 4. All right, let me check on those. All right, so I've summarized the results, and so we can kind of take a look at them. So I've written down the reversals and the number of cycles to failure, and this is for history A. I do need to point that out, that this is for history A. So we have a range of correct initiation lives in between 1.41 times 10 to the 5 and 9.07 times 10 to the 4 in cycles. So here we have 9.04 times 10 to the 4 all the way up to looks like 3.4 times 10 to the 5 cycles for that calculation from Manson-Halford. All right, so I think we're in the right ballpark here. I don't think I've done anything wrong with any of these calculations. Let me show at least the Neuber's rule calculation part for history B, and then you can do something very similar for history C. All right, so for this, we're going to go all the way back to our problem description page, in which history B goes from 0 to minus 480. So minus 480 kips. All right, so our nominal stress S, then, if we remember how that worked, is going to be from 0 to 48, actually minus 48 KSI. All right, so we're going to go and use our Neuber's rule again. Sigma epsilon is equal to KT squared times S squared over E. So for that, I'm going to go back to my spreadsheet. Let me just copy this into here. And I'm going to rename this to history B. And let's see. Now I'm going to use 480, my applied force. My nominal stress will be 48 KSI, and I'm going to use my solver to drive this to 0. By changing that cell. Well, that didn't look like it went to 0, so let me check this out. Okay, I think I had some wrong cells selected, so let me try this again, just to show you. So we're going to change M13. Let me make this some other number here. I'm in a stuck here, so let me sure what this is doing. Make this some other number, maybe 50. And now I'm going to hit the solver, and I'm going to change M13. I'm going to drive M13. Well, I'm going to drive this one, this one to 0 by changing this cell. And I think I had this checked. I think that might have been a problem. But I'm going to solve it, and it's driven it to 0. And I have a 71.478. All right. So because the initial excursion history B was negative, we end up with both compressive stresses and strains, minus 71.5 KSA and minus 19.311 microstrain. That's a really significant amount of strain. All right, let's go back and take a look at our history again. Okay, now this history goes all the way up to 480. So if I'm not mistaken, that is going to be a range of 960. And indeed it is. And so now I'm going to use, let me find my right page here. Okay, now I'm going to use my cyclic Neuber's rule. The delta epsilon, delta sigma delta epsilon is equal to KT squared delta S squared over E form of it. So I am going to go to my spreadsheet and I have a force range of 960. My nominal stress range is 96. Okay, and I'm just going to say maybe that's 50 for my initial guess. Now I'm going to use my solver again. And now I'm going to drive that cell to a value of 0 by changing this cell. Okay, and it did drive it to 0. So I have a stress range of 143 and 38,622 microstrain. All right, so let's see where we end up. Since this is an increase in load, we're going to both increase stress and strain. So I'm down here at minus 71.5. I'm going to add 143 to it. I'm at plus 71.5. And it looks like the other one is also double, but let's just check it out. I'm at minus 19,311. And now I'm going to add 38,622. So yeah, I'm at plus 19,311 microstrain. All right, now let's look at the next segment of our history. Now I'm at 480 and I go to 0. So that is a delta load of 480 kips. Let me scoot this over. Okay, 480 kips. Nominal stress range then of 48. And let me use my solver. I'm going to drive this line to 0 by changing this one. And it found a root. So it has 115.8. And a delta epsilon in microstrain of 11,916. And now that's probably overly precise, but we'll keep these values here anyway. All right, so this is a decrease in load. So now I'm at 71.5 and I take away 115.8. I end up at a minus 44.3. KSI. And let's see, I'm at 19,311 microstrain. I'm going to take away 11,916 microstrain. I end up at 7395 microstrain. All right, so I'm a little on the compressive side of the stress, but I'm still a little positive on the strain. Now, the next cycles are just repeats of the previous ones. So this will just keep cycling here, calculation-wise, back and forth. So from this, you should be able to calculate a maximum stress and a mean stress and a stress range and all those things that you need to do. So go back to the previous spreadsheet for the 3 strain life equations with modified for mean stress in order to calculate the number of cycles and reversals to failure, and then make the comparison with the test data that's listed in the text. History C is kind of the upside down version of History B, I think. Take a look at it here real quick. Okay, so instead of going 0 to minus 480, it's 0 to plus 480, and then it goes to minus 480. Okay, and now, well, it isn't quite the mirror image. So once it goes up, it goes from minus 480 to 240, and then cycles here. So what that's going to do is it's going to set up a different level of mean stress at the notch. And I can't tell you without doing the analysis if it could be a compressive mean stress or a negative mean stress. But you can do those calculations based on the same procedures that we did for the rest of the problem. And this is a fairly involved problem, but it's fairly typical of what you might have to go through for these kind of fatigue calculations at a notch. All right, so with that, I think that is good enough, and you can probably talk me into uploading my spreadsheet for you if you want to try that. All right, that's good for this one.